Hello students, and let's continue with the NMR spectroscopy once again. Before going further, let's have a quick recap of what we did in our previous video. So the main pointers from the previous video were NMR and its basic principle that we discussed about. We also talked about the effect of external magnetic field when a proton is kept in its environment. And then we talked about how do we get NMR signals, how do we get the spectrum of NMR, and then we landed upon the information that we can gather up from the spectrum of an NMR related to the structure of a molecule. So with these pointers in mind, let's continue further. Carrying on the discussion further, just as the number of signals in an NMR spectrum tells us how many kinds of protons a molecule contains, so the position of the signal actually help us to tell what kind of proton these are, whether it is aromatic proton, that means belonging to an aromatic chain, or a cyclic proton, or it is aliphatic ranging from primary, or it is a secondary, or it is a tertiary proton, or it is benzylic, or belonging to the allylic chain, or an allylic proton, acetylenic, whether it is adjacent to halogen or any other atoms or groups. So now these different kinds of protons actually have different electronic environments. And it is the electronic environment, as we discussed in the previous video, that determines just where in the spectrum a proton absorbs. So when I want to study the structure of an unknown substance, with the help of NMR spectroscopy, I take a small amount of the sample, keep it in the instrument, in the sample holder. So what happens actually after that? The molecule of that sample is placed in the magnetic field, right? So what is happening? Its electrons are caused to circulate, and in circulating they generate secondary magnetic field around them, that is called as induced magnetic field. So when this electron is moving, actually, so in the presence of the external magnetic field, which is B naught over here, this movement, this circulation generates an induced magnetic field. The circulation of electron about the proton generates induced magnetic field. Okay, now this induced magnetic field actually can be in such a way that it generates a field aligned in such a way at the proton that it opposes the applied field. So that means my induced magnetic field is just in the opposite direction of the applied magnetic field. Now what will happen? What will be the effective magnetic field which is felt by the proton? Why? Because this moving electron is generating an induced magnetic field in the opposite direction to that of the applied magnetic field. So the effective magnetic field which will be experienced by this proton over here actually will be diminished. It will be less in magnitude with respect to the external magnetic field which is applied over here, and this situation is called as shielding. shielding. This situation is called as shielding, and technically we say that the proton is shielded. So the proton is said to be shielded. Now on the other hand, if the circulation of electrons, specifically we talk about the pi electrons over here, okay, if the circulation of electrons about the nearby nuclei generates a field that can either oppose or let's say reinforce the applied field at the proton depending on the proton's location. If the induced field opposes the applied field, the proton is shielded, like just we discussed. If on the contrary, the induced field reinforces the applied field, means this induced field is now in the same direction as that of the externally applied field, then what happens? Then the effective field, the effective magnetic field which is experienced by the proton over here sitting inside will be greater than, will be augmented, and the proton greater than which field? Greater than the externally applied field, and the proton is said to be de-shielded. So in this condition, in this situation, de-shielding will be the phenomena technically called as. Okay. Now compared with a naked proton, a shielded proton requires a higher applied field strength, right? And a de-shielded proton will require the lower applied field strength on the contrary, just to provide the particular effective field strength at which absorption occurs. In other words, what I am trying to tell you is that when the shielding process is going on, then what will happen? The effective magnetic field which is experienced by the proton over here will be lesser as compared to the applied field. Now, my proton should experience a particular amount of magnetic field, but just because of this circulating electron, I am not able to give that amount of magnetic field to the proton. Why? Because it is being shielded. So in that case, what will happen? This proton will now require a higher applied field. Okay. Whereas on the contrary, in the case of de-shielding, it will be lower. Okay. So shielding, in other way, shifts the absorption upfield. So shielding will shift my absorption upfield, whereas de-shielding will shift my absorption downfield. Okay. Such shift in the position of NMR spectrum arising from the shielding and the de-shielding of the electrons, it is called as chemical shift. So technically this shift will be called as chemical shift. Okay. Now, how are the direction and magnitude, means the value of a particular chemical shift, can be measured, and how are they expressed? The unit in which a chemical shift is most conveniently expressed is parts per million. So it is expressed in parts per million, or ppm, of the total applied magnetic field. Now, since shielding and de-shielding, they are arising from the induced secondary fields, that means the induced magnetic fields. So the magnitude of the chemical shift is proportional to the strength of the applied field, or what is equivalent, proportional to the, let's say, the radio frequency, the field must match. Okay. So the reference point from which the chemical shifts are measured, actually for practical reasons, is not the signal from a naked proton, but the signal from an actual compound. Usually tetramethylsilane is taken, CH3 4Si. Why? The question arises, why only tetramethylsilane? Because of the low electronegativity of silicon. Secondly, because the shielding of the protons in the silane is greater than in most other organic molecules, and as a result, most NMR signals appear in the same direction from the tetramethylsilane, and that is downfield. Because silicon is surrounded by 4 methyl groups which are equivalent, which carry equivalent protons. And since they are equivalent protons, so we get only one single signal for this particular molecule. Now, the most commonly used scale is actually the delta scale, which is chosen for measuring the signal, and it is represented by delta. The position of tetramethylsilane signal is taken as 0 ppm. So most chemical shifts have delta values between 0 to 10, and it is -10 actually. The smaller delta value represents a small downfield, and a large delta value represents a larger downfield shift. Sometimes another scale is also chosen, which is given by tau scale, on which the tetramethylsilane signal is taken as 10 ppm. So most of the tau values, they lie between 0 and 10. The two scales are related to one another, and you can remember this as tau is equal to 10 minus delta value. So if delta is 8, you will get the value on tau scale as 2 ppm. An NMR signal from a particular proton appears at a different field strength than the signal from tetramethylsilane, and this difference, that is the chemical shift, is measured not in Gauss actually as we usually expect, but in the equivalent frequency units.